Welcome back to our class on machine translation. Today's lecture is on language models. That is both a very ambitious name, and when we go through it and finally end up with some language models, you might actually think that's a rather simple model we actually have there, but it's actually also really powerful. So before creating even more suspense, let's get just started. So language models answer the question, how likely is a string of English words good English in the case of English language models? So why are we doing this in the context of machine translation? Why do we need something like this? Because we have to produce a translation in the target language. And we have various issues to deal with, and the language model is going to help us with that. One of them is it is going to help with reordering. So it will look at a string of words like the house is small and say, well, that's probably a more likely string than small the is house. It also helps with word choice. So a translation model might not be sure about if the right translation for a word is home or house, but then if we're confronted with a choice between a sentence, I'm going home and I'm going house, it will prefer I'm going home. So we're going to do this in terms of probabilities and basically then make choices between alternatives and base it by which has the higher probability. So let's just define this problem. So n-gram language models have to deal with a string of English words. So big W is W sub 1, W sub 2, and so on, W sub n. So there are n words in a sentence. And the question is now, what is the probability of the string? So the reason why this is a hard problem, and this is actually also the most fascinating thing about language models, because they do a lot of work around this issue of sparse data. Many good sentences will not have been seen before. Actually, if you look at a newspaper article, you can probably think that probably almost all of the sentences in that newspaper story have never been written before because they talk about new events. So you can just collect statistics over all the sentences that are ever written or said in the world and then go with that. So you have to decompose that problem. So we're going to do this using the chain rule. So we're going to take the probability of this word sequence, word 1, word 2, word 3, word 4, word 5. And so here's the probability of the sequence. And we're going to break it up into predicting one word at a time. This is something that's going to stay with us throughout this entire course. The way we're going to deal with the problem of translation or other people deal with problems of language generation is always predict one word at a time. So we first predict the first word. So this is just the probability for the word one occurring. You could go fancy about it and saying probably if the first word occurring after the beginning of sentence token, if you introduce a special token like this, or maybe that is the beginning of sentence token. Then you go by probability of the second word giving the first word. And then the probability of the third word given the next two, and so on and so on. At the end, you have the probability of the nth word giving all the previous words. So in terms of simplifying the problem, we haven't really gained much yet because we said the probability of the whole sequence, it's going to be too sparse to estimate. Well, the last step, condition on the entire sequence. So if we just do a usual count-based estimation, well, we are probably not going to observe any counts for that whole sequence or the whole sequence without the last word. So what are we going to do about that? This is where the Markov assumption comes in. So the assumption is, well, when we make prediction, only the previous history matters. But the Markov assumption addition also says we only look at a limited memory. So only the last, let's say, k words, and k might be any number, are included in the history. So this is then called a kth order Markov model. I snuck in here the term history. So this is in language models, the sequence of words that we're conditioning on. So an example of a 2-gram language model, where we most look at word sequences to make predictions. Well, we start with probably the first word, then the probability of the second word given the first word. But then when we predict the third word, we don't look at the first word anymore. We only look at the second word, and we're ignoring the first word at that point, and we keep going. So this is called, confusingly, a first-order Markov model because we have a one-word history. It's also called a 2-gram language models because it looks at 2-word sequences. So there's a bit of a mismatch between the Markov model order and the n-gram language model, the n in the n-gram language model. So, what we're conditioning here is called the history. Mathematically, this is also an application of the chain rule. So this is a Markov chain because of that. How do we get these probabilities now that we need for the n-gram language model? Well, we just do fairly straightforward maximum likelihood estimation. At least that's what we start with. So we count how often have I seen the word sequence W1, W2, and I divide by the history. Here, the word W1, and go divide by the count of that. So all you need for this is large amounts of text and collect counts of large text. It's easy to get millions and billions of words of text. There's even, if you really want to go out overboard, you can get trillions of words of English if you just download the entire internet. Let's see how that works out. So here's some examples. So this is from our European Parliament corpus. And we just look at a bunch of sequences of words. So now we actually have a trigram language model or a 3-gram language model where we look at different conditioning contexts. Let's start with the green. That occurs quite frequently in the corpus, over 1,000 times. And what is followed by it? I mean, it's a bit of characteristics of the corpus that here the most frequent word are following the green is paper. So the green paper, the green group, the green light, the green party, the green ECU. So this is what's following the green. And you can look at the counts here. So for paper, the count is 801. And therefore we divide 801 through 1748, and this is the number we get, and that's the probability we assign to this n-gram prediction. To predicting the word group, this is the probability, and so on. Okay, let's look at a few other words sequences. So the red, what follows the red? Well, cross, the red cross, the red tape, the red army, the red card. And then let's look at the blue. Well, the blue box, the period, meaning apparently the sentence ends there, out of the blue. The blue flag, the blue, comma, maybe that's similar to the period. The blue angel. So these are the words follow there. The blue is much less frequent than the other occurrences. So you already see you also have very few counts for the trigrams. So the blue angel occurs 3 times. It's still the 5th most likely n-gram. So down here you see also spelled out how we did the computation for the red cross. 225 trigrams in the European corpus start with the red, and 123 of them end with cross, and that's how you do this calculation. That's pretty straightforward. So let's immediately look at how we're actually going to measure the quality of our language models. It's generally a good principle if you do any kind of research project in natural language or elsewhere, is very early ask yourself the question, how do you measure success? That is going to guide a lot of your decisions instead of just going by intuition all the time. So this is our general idea. A good model assigns a text of real English W a high probability. You could also say a good model assigns a text of jumbled English a low probability, But that's a bit harder to measure because where do you get jumbled English from? But you can get a lot of real English very easily. That's where you got the original training data from. So this can be measured with cross entropy. So we introduced entropy before. So we basically take it's basically just a fancy way of converting the probability for the word sequence into a slightly different number. So we look at the word sequence and the probability that is assigned to the word sequence. The log, we now kind of in the mathematical realm of entropies. So if you remember the definition of entropy, it had something to do then with the p, the probability times the log of the probability. Well, we actually don't have to now go over the probability of each word in this each prediction because we have n number of predictions. And so we are just going to divide by 1 divided by n. So this is roughly an entropy formula, which we feed with a real English. So the model, so there are two different things going on. There's the model that we have estimated, so p, and then we have actually a real word sequence of words that should not be part of the training data to measure it. So that's cross entropy. That's a fairly broadly used concept in assessing how well you'd predict sequences. We actually also use this at some point later in neural machine translation as kind of the dominant way to measure, to track progress. And then there's something that happened in the language model world, which is perplexity. It's 2 to the power of that, so it's not really a major reformulation of it. It gives you bigger numbers. I heard someone who talked about language models decades ago saying that's actually the main reason you get bigger numbers, and you can claim more easily success by making differences on big numbers than on small numbers. But they're also a bit more readable numbers. Okay, let's play this out. So these are trigram language models, actually slightly sophisticated than what we had talked about, but we'll just look at it now in the context of how we evaluated that. There's actually a lot of interesting stuff going on here. So as you see, everything is lowercase, so the word I here at the beginning is actually lowercase. And we also have these special tokens, end of sentence, beginning of sentence. So between two sentences, you insert an end of sentence and beginning of sentence. So when you predict the first word, you predicted conditioned on that. There's no point in predicting the beginning of sentence because the beginning of sentence always occurs after the end of sentence. So predicting how likely does a sentence start with the word I. And in this particular corpus, it's 10%. That's pretty high, but this is the European Parliament proceedings. People give speeches, people talk about themselves. Newspaper text, you will see the word I being much, much rarely used. And it's not going to be 10% probability of sentences start with I. In natural human communication, probably the word I is quite prominent. Then the word would following I, also 14%, pretty likely. I would like, that's a fairly nice, I would like apparently is the most common thing that follows that. And I would like to, that is almost a requirement. I would like to, if I follow it with a verb phrase, the word to has to follow here then. And then I would like to commend. Now that's a very odd word, even for the European Parliament, and it has a very low probability. And we can keep kind of going to, I would commend that's pretty likely. Rapporteur is a really odd word too, but when you talk commend something, apparently that's what you do with the rapporteurs, you're commending them. And then on his work, period. And then the end of sentence token follows the period is almost a certainty. So these are the probabilities. And then in the right column, we have the negative log probabilities, basically just a mathematical conversion. So these are not surprisingly higher number whenever you have a lower number on the left. So what are the extreme values here too? That was one of our safest predictions. That's almost 0, while commend was on one of our unlikeliest prediction, and the negative log of that is much higher. So this is what we're going to do now in computing the entropy, the cross entropy. So we're going to take all these values and basically average them up. So we add them up and divide by the number of them, divide by n. That gives you then this number here. So this is the cross entropy for this particular, if we would take this as a test sentence for our model that we have here. Okay, let's look a little bit at the numbers because they're kind of interesting about the power of n-gram language models and what are they good at predicting and how much context they need. So what we're comparing here are language models of different sizes. So a unigram language model only predicts a word without any context. So it has a history of 0 and 1 word prediction. So it's a 1-gram language model, unigram language model. This is the language model we did earlier all our math over. We predict on a history of 1 word. This is the one we just had. So the numbers actually, if you check with the previous slide, are the same. And here's an even more powerful one that looks at 4-gram. In practice, up to 5-gram language models are commonly used. Okay, so predicting the word I here is without any context. How likely is the word I occurring anywhere? This is, again, the negative log probability. So that is the word I doesn't necessarily appear all that often, but as the beginning of a sentence, it actually appears more likely. And that's a trend you see with all these numbers. So if you go from left to right, you see all the numbers decrease. Let's look at the next one. So would occurring by itself, 8.3. Following the word I, 2.8. That happening at the beginning of a sentence, 2.79. And here we actually don't add any additional context because we only have 2-word history so far. So this doesn't get any better. Many other striking things here. The rapporteur, this really odd word following the, well, yeah, a noun following the is probably a good place for it to be put. And here now the comment that really helps a lot in predicting this word. Okay, so if you look at these different n-gram language model and you take now the average of these negative logs, this gives you cross entropy. And you see this number going down with the bigger the language model gets, and perplexity is 2 to the power of that. So you're getting much bigger numbers. So as I said, these are bigger numbers that might be nicer to deal with. Okay, this was the basic introduction. First of all, how we're going to do the language models and how we're evaluating them. So let's get into the gory detail. So let's see, there are some n-grams in our corpus that we have not seen. So let's say I've seen this sequence of words that I like to in our corpus, but I've never seen I like to smooth in our corpus. So we did maximum likelihood estimation, and that tells us that probability is going to get a value of 0. So that's what we've done so far. I didn't have a problem with so far, but here's where the problem comes in. Any sentence that includes I like to smooth will be assigned a probability of 0. Again, remember, chain will be multiplying up these probabilities. So if you have a factor of 0 in there, then the whole product becomes 0. So that's not good. So any sequence that has an unseen n-gram in it is going to get a probability of 0. That's also going to create all kinds of havoc for perplexity and cross entropy calculations because, yeah, what's the log of 0? That's not going to work. Okay, so what are we going to do? Well, let's just say for all possible n-grams, just add 1 to it. To all the actual counts, we add 1, so there are not going to be any zeros. Still, kind of the things that occur rarely occur, have lower counts. We just add consistently 1 to every count we see. So since we're adding 1 to every count we see, we also then have to increase the denominator here and this is, since we're counting for each vocabulary item, so V is the vocabulary side. For each vocabulary item, we're adding one count. We're pretending you've seen it. This increases then by the size of the vocabulary. So this the count of the history plus the count for vocabulary. So here's a problem. In any kind of practical model, even for the bigram models we're going to talk about first, there are many more unseen n-grams than seen n-grams. So if you look at the square vocabulary, if you look at all possible word pairs, the vast majority of the word pairs are actually not possible or not occurring ever in text. And here's an example for the European bigrams. So we're just looking at word sequences, 2 words. There are 86,700 distinct words in it. It's a corpus of 30 million words. We went over the whole Zipf's law. We also know that about 30,000 of them are just words that occur exactly once. So how many bigrams are there? Actually quite a lot, 7 billion, 7.5 billion. So that's quite a lot. And this is in a 30 million word corpus. So there are 7.5 billion possible bigrams. There are only 30 million words and therefore 30 million bigrams in the corpus. If you just add up, then the counts that we actually consider, so this +1 is basically adds up to all this. So we're gonna add a massive number of counts for things we actually haven't seen. So, okay, 1 is just a number we just came up with. Just find a smaller number. It's just some smaller number. Let's just add that smaller number in there, maybe some fractional count, maybe 0.1 or whatever. And go with that so that we can then discount a little bit this massive amount of unseen n-grams. So here's a question. What is a good value for this alpha? How do we find it? So one way we can do about this is optimize it on a held out set. So this is how we're going to do this. So let's say the 2-gram red circle occurs in a 30 million word corpus exactly once. So let's say this is one of these bigrams that occur exactly once. So maximum likelihood estimation would be just kind of the raw of the probability for that. It's 1 out of 30 million. So we're not estimating language models, we're just estimating the probability for this bigram. But we would expect it to occur less often than that. Why is that? Well, because there are unseen events that we expect to occur. So if we expect unseen events to occur, it means all seen events have to occur less often. So how likely does a bigram that occurs only 30 million words in a corpus occur in the wild? So here is how we can find that out. So we're gonna basically get a list of all these bigrams. Red circle, funny elephant, I don't know, any kind of things that occur exactly once in our corpus. So we call this big N sub 1. Now we're gonna get another 30 million word corpus and check these words, these bigrams that occur once. How often do they occur in that corpus? So we want to know how much we can expect them to occur. Well, let's just check on another corpus how much they actually occur, and that gives us a good sense on how much we expect them to occur. So some of the bigrams occur 0 times, some of them, next one maybe also 0 times, next one 1 time, next one 0 time, but maybe this one occurs twice in that other corpus, and so on and so on. So this is all all the kind of counts we actually see for these bigrams that in the first corpus occurred once, how often do they occur in the second corpus, and that might be a different number of times. So we will take the average of that, so we divide by n, and this is our test count. So here we do this. We first came up with these adjusted count statistics. So something occurs 0 times. If you just add up, this is the probability for it occurring. If something occurs once, this is the probability for it occurring, and so on. So these are adjusted counts. Here we kind of did a different adjustment. I'll get to that in a second, why we choose this particular alpha. And here is the test counts, the method we just went over. So things that, all the bigrams that never occur, there's a massive number of those that never occur. On average, they occur 0.0016 times. So a few of them will occur, and maybe a few of them will also occur more than once, but the vast majority of them will actually also not occur in another corpus. These are the things that occur once in a corpus, 0.46. These are the things that occur twice in the corpus, and you can see it tends to be always slightly below the number for things that occur 20 times. In our first corpus, on average, they occur 18.9 times in that second corpus. So these are kind of our model that we want to come up with. So, so the first idea was to add one. That's the add one smoothing, and you can see that it massively overestimates the probability for bigrams that occur. Never in the first corpus, 0.00378 doesn't look as big, but this is what you compare it with. And in practice, you waste all your probability, almost all your probability mass on that. Because already for the things that occur once, that we still expect to occur about half of the times in the other corpus, we only have now 0.0755 left. And if you look at this number here, that's just kind of, things got completely off the rails. Things occur 20 times, we now expect it to occur only 0.07931 times. Okay, so, okay, one is definitely not a good idea. Let's add some alpha, and the alpha we're adding here is 0.00017. We're choosing this, so these two numbers here match up now. Okay, so these two numbers match up, so that's good. Things that occur once, okay, slightly discounted, not as much discounted as in reality, only 0.95 versus 0.46. So the bigrams only slightly discounted, and so on. However, and so we kind of go over that over time. Okay, so this seems to be a reasonable step. The numbers are not too far off, but they are somewhat off. But why don't we just do things that we just did? Why do we have to come up with a formula to discount or upcount actual counts? Why don't we get the true counts from held out data as we just did for testing purposes? So this is kind of the setup for that. It's called deleted estimation. So we take a corpus, so we need to get the corpus, and we need a held up corpus. Well, we have one corpus, so we're going to split it into two halves. One is called training, and the other one is held out. Then we collect the counts of the training corpus. So then we know for n-grams that occur r times, first of all, how many are there? So that's big N R. And then we can look for the n-grams that occur r times. How often have they been seen in the held out data? So the second half of the training corpus. And it's T sub R. So why don't we just say that's our held out estimator? So we can take this T sub R and divide it by the NR and N, where the count here, R, is the count of the n-gram in the original corpus. So obviously this wastes half the corpus, because one and a half is corpus we actually collect counts that we're going to use for our language model. The other one is really just for validation to assessing these probabilities. But hey, we can go in both directions. So if we switch then the role of these two halves, we get an equivalent count. Let's call it T sub R1 and T sub R2, and we just kind of then average between them. So that's one way you could go about it. Another way to do it is good Turing smoothing. So it comes up with a magic formula that tells us how we should discount things. And right here in the middle is the magic formula. So it operates on these n sub r statistics that we have, how many words or bigrams occur once, how many occur twice, how many occur 3 times. So this is what nr is. So r is the number of times something occurs. N is how many words occur that oftentimes. So we already had n1, how often do things occur that occur once, and so on. So nr is the number of n-grams that occur exactly r times in the corpus. We're also going to come up with n0, obviously the number of times that occurs 0 times in the corpus. Well, that is, we're going to use the total number of n-grams. So this formula seems to fall a little bit out of the sky. The math to derive it is not super simple, but there is a derivation in the textbook Statistical Machine Translation where you actually can find out how this formula comes around. So if you're mathematically inclined, interested, and curious, that's actually rewarding to kind of go through that, how we come up with formulas like that. So how well does good Turing smoothing work? And it actually works impressively well. So here is basically the same thing we did for the +1 and plus alpha smoothing. So on the right here, we have the test counts. We're basically on a held down test set. How well do we do? Here are the adjusted counts according to good Turing smoothing. So these are stars. And you see the numbers are really close. So 0.0015, 0.0016. This is almost identical. So there might be 1 or 2% off relative. By the way, here are the n sub r's, so the n numbers that go into that formula. So this works really well. So good Turing smoothing is kind of a go-to method, and we're only going to later look at even more sophisticated ways to handle this. Next, we're going to look at the smoothing and how to handle sparse data from a slightly different angle that is specific to n-gram language models. So in a given corpus, we might never observe these sequences: Scottish beer drinkers, Scottish beer eaters. Both have count 0, so by using count smoothing methods, that 0 will be adjusted to some really low value, so both of them are gonna be very unlikely but possible. But I think our sense at looking at these n-grams, we don't really like these beer eaters here at all. And why don't we just, base our estimates not on this Scottish beer eaters, but just on the bigram. So instead of having doing our assessments over the trigram Scottish beer eaters, why don't we just go by the bigram? So this is the idea of back-off. So we want to have a trigram language model that takes a rich history of the 2 previous words into account. But when that ends up with 0 counts, we're gonna back off to bigram language models. So we can estimate a unigram language model, a bigram language model, and a trigram language model. So the question is now, how do we combine that? So the first naive idea is to just interpolate that. So the higher and lower n-gram models have different strengths and weaknesses. The higher order n-gram models are sensitive to more context, but have sparse counts. And the lower order n-grams consider only very limited context, but have robust counts. So if you combine them, so we literally just weigh each of these, the unigram language model here, the bigram language model here, and the trigram language model, we just weight them with these lambda values. They have to add up to 1 to make this a proper probability distribution, and that's our interpolated language model for a trigram. So in our case, with the beer drinkers, here we still considered the Scottish beer drinkers. Here we only consider beer drinkers. And here we only now looking at drinkers. So a slightly different way to do this, and it's going to lead into the way we're going to do things in the future, is kind of define this as a recursive process. And we're going to be a bit more sophisticated about it by also estimating these lambdas, where we just previously said we have a flat lambda value for the unigram, bigram, trigram. We're going to take some statistics over the sequence that we're backing off from into account. So some of these histories we can trust more than others, and some we can't trust as much. And we should make the backup sensitive to that. The big idea here being, if I have seen a history many times, then seeing 0 counts probably indicate this is an unlikely event. But if I ever seen a history only really rarely, then I don't really trust much its predictions, so we should really back off more frequently. So this lambda should have something to do with probably the frequency of that history. Let's go into that in a bit more detail later. So this is at the bottom is, unfortunately, the math gets a bit convoluted as written down here, but it's a pretty straightforward thing. So we have this n-gram language model that considers the previous word. So we're predicting the word wi here. So the last word in the history before that is I minus 1. And this is the earliest word in history that we pay attention to, which has something to do with the n of the n-gram language model. Okay, so that's the sequence we're predicting, and we're going to have a specific back-off value. So this is now how much we trust that prediction that we get out of our unsmoothed, unbacked off model. And then this is how much we trust the back-off. So what's different here is, here we're going to start by this word here, and here we start by the next word. So we removed this particular word here from the history. Okay, so let's do one way of doing back-off, which is, let's just trust the higher order language model that contains the n-gram. So this is the idea. So if the count, if I reach a count that is not 0, that's where we stop. Otherwise, we kind of go down the rails. So this is our back-off language model for that word sequence. And this is the previous probability distribution. You have to be a bit careful about this. And I say that in a second. So we're not going to call it probability distribution, and there's a reason for it. So if the counts are larger than 0, we'll just go with that. So it is basically a probability distribution. But the reason why it is not a proper probability distribution is if these values can't add up to 1. If we just add up all the things where the count is larger than 0 and that adds up to 1, and then we still add some probability mass or something else, we're going to end up for the actual probability distribution we want to estimate with counts that are bigger than 1 and then can't be right. So there's alpha, all the possible predictions for all these possible words where the count is larger than 1. That can't add up all the way to 1. Something has to be left over. And that something that's being left over is actually very clearly spelled out here. That's this value. So this is how much probability mass we reserve for events that we haven't seen. And then it's kind of a recursive calculation where we then go for the back-off probability distribution with one order smaller. So what do we have to do? We need to have adjusted prediction model here, and we need to have a discounting function. So the adjusted prediction model might just be vanilla maximum likelihood estimated model, but overall it's going to be discounted somehow. So we need to figure out some way to come up with this discounting value. Let's combine the idea of back-off with the good Turing smoothing that we introduced earlier. So again, we start with kind of the basic idea of how do we do conditional probability. So we do the count of the word sequence, word 1, word 2, and divide by the probability of the history. Here it's just the word 1. So the counts we usually collect over the data. Some word sequences occur once, some occur 5 times, some occur 100 times. And good Turing allows us to take these counts that we actually collected over the data and convert them into expected counts. These expected counts are going to be smaller than the actual counts because we have to save some probability mass for unseen events. So we are discounting everything a little bit. So now we're going to use these expected counts to come up with a prediction model. So this is the prediction model, this alpha, that is now based on adjusted counts. So this, if you now sum this up over all the W2s, this is going to be less than 1 because we discounted each count, so there's some probability mass left. So if you sum this all up, it's going to be less than 1, so 1 minus something, some probability mass is going to be left over. And that gives us this discounting value specific to this particular history, W1. So let's actually do this in practice on one example here. So let's say we have the word, this is like a tiny, tiny corpus. So we have the word A, this is the history we're dealing with, and it's followed in the data we observed by 3 different words, big, house, and new, and the counts are 3, 1, 3, 3, and 1. So this was kind of the naive probability distribution. Here still everything adds up to 1. And this is our magic good Turing discounting formula we got from large statistics over the corpus. And it says, well, whatever occurs 3 times, we really just expect it to occur 2.24 times in new data. And everything we've seen once in the training data, we expect it to see only 0.446 times in new data. So this is the counts we're going to use now for discounting. And these are the values came up with. So instead of 0.43 for the things that occur 3 times, it's now 0.32. So that, if you add that up and subtract it from 1, we're left with 0.3 for the back-off. So this is then how much probability is left for the back-off, and the back-off here in this case is then a unigram model. So there's one kind of tiny note here that if you do this properly, the D2 actually has to be slightly higher than that, and that has some technical reasons, not entirely obvious first, but then probably pretty plausible. We never back off to a prediction that we're going to predict the word big, or that we predict the word house, or predict the word new. So in the back-off probability distribution, that probability mass would be wasted in the unigram probability distribution. So we kind of need to push that back into the combined probability distribution, and we do this by increasing D2. So this is a pretty neat solution to our problems with sparse data. Let's go get even more fancy. So let's also consider the diversity of predicted words. What does that mean? Consider the bigram history spite and constant. So what words do I predict from the history spite? Which words do I predict from the history constant? I've chose these two words because both of them occur equal number of times in the European Parliament corpus. They both occur 993 times. However, only 9 different words follow the word spite. Actually, it's almost always followed by the word of in the phrase in spite of. That's kind of the word, how the word spite is used. It's rarely used otherwise. However, the word constant is followed by 415 different words. This is a word that occurs 993 times, and it's followed by 415 words. There seems to be almost no consistency in what follows it. And if you look at the most frequent ones, it's words like and then constant concern 27 times. 27 out of 993. That's not much. That's less than 3%. Pressure, constant pressure. So it seems like the word constant can be followed by almost any word. There's a huge tail of singletons, 268 words occur only once following constant. So what does that mean for our back-off considerations? So since the word constant is followed by all kinds of words, we would more likely to expect a new word following constant. While spite, we're pretty much sure that the word of is going to follow and everything else is going to be weird. So we are more likely to see new bigrams that start with constant than with spite. We almost expect when the word constant comes that there's a good likelihood that a new word follows it. While in spite, we're just really going to expect the word of following it. So there's a technique called Witten-Bell smoothing that considers the diversity of predicted words. So here is the math for it. It's also an application of recursive interpolation. So the one mathematical term we're going to introduce here newly is this one here. This says number of words that occur one or more times in the sequence. So following W1 to Wn-1, these are specifically chosen words. And then here is our placeholder. So how many words are following in this sequence? Basically what we just did. These are the statistics we just computed. So how many words follow more than one time the word spite? That was only, let's peek back again, 9 different words. While for the word constant, this was 415 different words. So these are the numbers we're going to have here. So here's the mathematical definition. As the size of the set of words, set of n-grams that occur more than any number of times, and that start with that particular sequence of words. Okay, given this, this is the formula that we then use to set the lambda parameters for interpolated back-off. So it basically does back-off weight assigned to this number here. So this is, in our case, this 9, or what was it, the other number again? 415. This is the 9 or the 415 for the two choices of a spite and for constant. And this is down here. That's the total number. So this was the 993, if I still got that right. Yeah. Okay, here's actually numbers actually filled in and the computation fully carried out. So this is how it looks for spite. So that was this 9 that we add to the 993 at the denominator. Here, very little weight is given to the back-off. While in the other example with constant, so we divide that by that, actually almost 30% probability is given to constant. So what this means in practice is that if you see the word constant, with 30% probability, we actually now expect to see a word we haven't seen before in our training data. And that is not completely unwarranted by the statistics we had. Okay, let's look at the whole thing from a different angle. So this is the same spirit of ideas, but we're now going to look at it from the other direction. So consider the word York. It's actually a fairly frequent word in the European Parliament corpus, of course 477 times. It's as frequent as other words like foods and indicates and providers. It's a common enough word. So in a unigram language model, it gets a respectable probability. Basically 447 divided by total corpus size. It's not the most frequent word, but it's not a completely crazy word. However, in the corpus almost always follows the word new in the phrase New York. There's also an English city of York. Apparently that's only mentioned 4 times. So 447 times it's New York, and 443 times, and 4 times is the English city of York. Okay, that's an interesting fact. Another classic example is Kong in Hong Kong. Okay, so what does that mean? We're talking here suddenly about unigram language models. Why do we care about unigram language models? We care about unigram language models because we back off to them. So if the bigram model is inconclusive, then we're going to back off to the unigram model. However, York is an unlikely second word in an unseen bigram. We don't expect York to occur in new contexts. We expect York to follow new and otherwise not really occur much. So in a back-off unigram model, York should have a low probability. In a naive unigram model, it's going to have this 447. It's going to have the same probability as foods, indicates, providers. But when used as a back-off, we don't expect to back off to predict the word York out of the blue, like we would expect the word foods to be predicted out of the blue. So this is the intuition behind Kneser-Ney smoothing. So Kneser-Ney smoothing takes a diversity of histories into account. So we basically have a similar thing that we just noticed in Witten-Bell smoothing, just the other way around. So we kind of look at how many different contexts does this particular word occur in. So how many words are there so that you have a bigram where that particular word and the word in question follow each other. How many of those are there? Again, for York, that would be, well, we don't know for sure, probably 2, 3, 4 times. But for other words like foods and so on, it's probably higher than that. So usually you would do maximum likelihood estimation of a unigram model just based off the counts. But in Kneser-Ney smoothing, we replace the counts with the count of histories. So this number here. So there's a slight modification to that called modified Kneser-Ney smoothing that's based on basically the interpolation mechanism. So you have a back-off distribution, then you have this the adjusted probability distribution where you reserve some probability mass for dn, and that's what you back off to. So this is just the layout for interpolation. So it requires this back-off distribution and it requires a discounting value. So in a modified Kneser-Ney smoothing, we now first come up with a fancy method to come up with discounts. And the way we do discounting now, it's slightly different. So we don't just go do Turing smoothing. and just counts this way, and that leaves us some probability mass. Now we actually subtract a value from every seen count. So if something's seen once, we're going to say it only occurs 1 minus something. And these are now, you need to come up with some kind of values. So you have to have 3 values, D1, D2. And then we're just going to have a value for all the counts bigger than 3. So there are very specific discount values you have to choose. We still haven't said yet where we get them from. Otherwise, this probability distribution is actually not using good Turing smoothing. It just is, it's just a count-based probability estimation where just the discounts are applied. So here are magic formulas. There's actually quite a lot of math to back that up on why we arrive on these particular values. It's the same kind of mathematical reasoning that is behind good Turing smoothing. And again, whoever's inclined, I'm actually encouraging you to look into that. It's in the textbook. So it's all based on the same kind of raw statistics that good Turing smoothing operates on, like how many n-grams occur 1 time, how many n-grams occur twice, and so on and so on. And then it basically counts and computes discount values based on that. Here the formula for the discount mass that was set aside from discounting of the highest order n-gram model. So that's the formula in all its gory detail. Just keep in mind what's going on here is there's certain n-grams that occur maybe once, and you discounted D1 from it, so you have to add up all that. There is all the ones that occur twice, and there's the count of them, and the discounting value for that, and then the ones that occur 3 or more times. And so we basically add up all these discount values that we subtracted from the actual counts. So divided by the total number of how often any n-gram occurred in that context, that's a discount value. Here now the formula for the lower order n-gram models. So this takes into account what we just talked about. So we talked about the diversity of histories a particular word might appear in. So this is what we talked about earlier. So for the word York, that's not many. For other words like food, that might be quite a lot. So this is what we're going to now base the estimation of the lower order n-gram models on. So we're not going to base it on the raw counts for a particular n-gram. We're going to base it on the number of different histories it occurs in. So this would be for York much smaller than for food. And we're going to do this not just for the unigram model, you also do it for all the lower order n-gram models besides the higher order language models. So for 5-gram language models, we would do this here for the 4-gram model, for the 3-gram model, for the 2-gram model, and the 1-gram model. All things we back off to. Then we also have the discounting. So this is the usual discounting. We have 3 different values as before, D1, D2, and D3 plus, based on the count of the histories. This is just kind of then the final piece of getting the probability mass for the amount for back-off. And this is just basically the sum over all the discounts we collected. Okay, I hope your head doesn't hurt too much because we have one final twist, but this is really the last slide on all these methods. Interpolated back-off. So we talked about interpolation and we talked about back-off. We kind of forgot about interpolation. Interpolation was the idea, let's just take a unigram model, a bigram model, a trigram model, and just weight them somehow and combine them. But then we backed away from that and went to back-off, where we said, we're going to use the highest order n-gram model where we have a positive count for that particular n-gram and then go with that and then stop there. But now we say, well, let's just add in the back-off in any case. So the problem with that is we stop if the n-gram occurs more than 0 times. But if it only occurs once, that's not a super reliable statistic. So if it's sparse, it's not very reliable. So 2 n-grams with the same history occurring once, they get the same probability. One might be an outlier, the other one is just somehow underrepresented in training data. To remedy this, we always consider the lower order back-off models. Adapting the alpha function into interpolated alpha I function by adding back-off. So here is how we do this. So this is now our new alpha. This is alpha as we computed before. It doesn't look too complicated. You're just going to always add in the back-off for that as well. So the D function needs to be adapted as well, so things make sense, don't get out of hand with probability mass. Probability mass still has to add up to 1 at the very end. So big idea here is we're always going to also consider the back-off statistics. Okay, how good do these things work? Here's some perplexity numbers of language models trained on the Europarl corpus. And we're going to do bigram models, trigram models, 4-gram models. Not entirely surprisingly, the more history we can take into account, the better the models get. So the perplexity goes down for pretty much all these methods. And here are the different methods we talked about. One is just doing good Turing smoothing. So we just discounted counts and saved the discounting value based on this magic formula, and then use the discounted values for the back-off. This is Witten-Bell that took into account the diversity of histories, that some words like constant have many possible words that follow it, while words like spite don't. This is modified Kneser-Ney, and the final thing is the interpolated modified Kneser-Ney. So this is the Kneser-Ney method that also always interpolates with lower order models. And that seems to be the most successful. But one story also seems to be that, yeah, I mean, 4-gram models, you should have as much history in them as possible. Let's round up this lecture by looking a little bit at efficiency and how to implement these models. So basically, these models have to store numbers for any n-gram seen in training. I alluded to, well, they're trillion-word corpora. We can estimate models of a trillion-word corpora. So any n-gram that occurred in a trillion-word corpus, that will get very big. So what can be done to make the whole thing efficient? So we have millions and billions of words that are easy to get, or trillions of words of English. And then you get big models, and the huge language models don't easily fit into RAM. So how big do these things get? So this is just some statistics on n-grams occurring in the Europarl corpus. So it's about 30 million words in there. But there are only 86,700 different words. Of those, 33,000 are singletons. Zipf's law should ring in the back of your head there. Bigrams, there are 2 million different bigrams, but 1.1 of them, 1.1 million, are singletons. That's 48% of all observed bigrams are singletons. And it just gets worse and worse. For 5 grams, I mean, this is almost as big as the corpus. The corpus is 30 million, almost 30 million words. There are almost 20 million different 5 grams in there.
and the vast majority of them is unseen. So this is actually pretty striking when you consider a 5-word sequence. So it basically says if you say a 5-word sequence, there's a good chance that nobody ever said that 5-word sequence before. So one way to deal with the size of language models is to remove singletons of higher order n-grams. So maybe not the unigrams and bigrams, but everything above that. That's going to reduce the size quite a lot. Another way to save memory are efficient data structures. So this should be dear to the heart of every computer scientist. Consider the case that you might have to store probabilities for the very large majority and the very large number. Both share the history, the very large. So there's really no need to store the history twice. So the idea is to have a trie data structure that first indexes things with the word the, then very, then large, and then you have here the two possible choices, majority number, and this is then where you have these log probability values. And another thing you store along the way are back-off values. So these are data structures that are used to store language models. Another trick is to reduce the vocabulary size. So each number is treated as a separate token. There are infinite many numbers, so if you have very large corpora, you're going to have massive amounts of numbers. It's actually not unusual when you have really large corpora and just go by the vocabulary, that the vast majority of vocabulary at that point becomes either names or numbers. So you could replace all the numbers with a particular token num, but if you want to be a bit more careful and still prefer that I pay 950.00 in May 2007 over I pay 2007 in May 950.00. If our translation model has to distinguish between the two, we still want to prefer the first one. And so it's not, if we just replace them with number tokens, they would be identical. But if we just kind of replace each digit with like a special symbol like @ or since we're replacing all the digits, why not take one of these digits as a special token? And then we're going to get this here. And you will see that May being followed by a 4-digit number is a pretty common thing to do, but May being followed by a fractional number is rather unusual.
That's it for today. So we considered the problem of language models, which we defined as how likely is a string of English words good English. So we want to assign probabilities for all possible English word combinations and saying which ones are fluent. That's going to help us with building machine translation systems that produce fluent output. You want to produce English that is good English. We framed this problem as n-gram language models using the Markov assumption to reduce the size of the history, and then looked at the evaluation in terms of complexity and went through various methods in quite some detail, and at the end looked at managing the size of the model. So this is the language model. It's a fairly powerful element of any kind of natural language task, not just machine translation. And in the next lecture, we're going to look at a simple translation model.